Okay, so the formula then for voltage division is basically Vx is equal to Rx over R total multiplied by V total. And so basically what we're saying is that the voltage drop across any individual resistor is equal to the ratio of that resistor to the total resistance times the total voltage. So these resistors will drop the voltage proportional to their size in comparison to the total. Okay, so what that means basically then is that we need to start off by finding RT. And so we know that RT is equal to R1 plus R2 plus R3 plus R4. And again, I apologize for the fact that that's a bit messy. But, it should be legible at the very least, I suppose. And it's hard, doing that with the mouse. And I think I'm getting a bit better at it as I go. But so we got, and we'll leave this in K for now. So 1.0K. And I'm not going to bother to write down the ohm symbol again. And there is my decimal in there, it's not very big. Plus, we got 6.8K. Plus 1.4K. And I got a problem with K's. These should be lowercase k's, but a lot of times I can't distinguish between them. And so they might look like uppercase K's, but kilo should be lowercase k. Not that that's a real big issue, I suppose. And 3.3K. So we have the sum of 1K, 6.8K, 1.4K, 3.3K. And so RT now comes out to be 12.5 K ohms. So using the voltage division formula, I should be able to say now that V1 is equal to R1 over RT multiplied by VT. And so I have 1.0K. And so, I can leave out the K's now and do 1.0 over 12.5, right? The K is going to cancel with the K anyway. And so, when you're putting that in your calculator, you don't have to put in 1,000 and 12,500. Put in 1 divided by 12.5 and multiply that by 25 volts and come up with V1 is equal to 2 volts. Now, so next, V2 is equal to R2 divided by RT and multiplied by VT. And so we have 6.8K over 12.5K. Now you'll notice then that the 6.8K is more than half of the 12.5K. So therefore we expect that the voltage drop across V2 is approximately, or a little bit more than, half the voltage of VT. And so when we do the calculation, we're going to verify that, of course, we come up with 13.6 volts. And so remember now that in this one, right, when you divide 6.8 by 12.5, you're not getting a nice rounded number. And so make sure that you keep 3 significant digits and that you round appropriately, which means you know, if you got to round that up to 13.6, you should do that before he gives me a final answer. Okay, so V3 then now will be equal to R3 at 1.4K divided by RT at, again, 12.5K and multiplied by VT at 25 volts. And so V3 then, if you do that calculation, we're coming out with 2.8 volts. Now, and so you notice that I just went ahead and calculated these as V1, V2, and V3, and I didn't really label the resistors. And so let's think about the fact that in this circuit, whoever drew this and presented us didn't label anything up here. So we might want to say that, well, of course, this is VT, and we might want to stick labels on our resistors, because I just went ahead and assumed that the first one is R1 and the second one is R2 and so on, right? And so be a bit more specific now. Would be a good idea perhaps for us to label them R1 through R4. I guess it was straightforward what I was doing, but I didn't really say it, right? And so now the last remaining voltage then, V4, we could find that using KVL as the difference between the 25 and the sum of V1, V2, and V3. But because this said voltage division, we'll go ahead now and say that V4 is 3.3K over the total, which was 12.5K times the 25 volts, and come up with V4 has a value of 6.6 volts. And again, you know, it's always good to verify that KVL holds, and so make you think that you don't have any mistakes made. And so for V1 now, we had 2 volts. For V2, we had 13.6 volts. For V3, we have 2.8 volts. And for V4, we have 6.6 volts. Now, if there's a rounding error, you might not get exactly 25, but in this case we do, right? And we add that up, we get 25.0 volts. And just let me move that 0 over a bit closer. 25.0 volts. And so then that means, of course, that KVL holds true, right?